This is the answer to homework 5, number 1. We're given that x and y are independent, that density of x is equal to ux minus 1 minus ux minus 2, and fy is equal to uy minus uy minus 1, and z is equal to x plus y, and we need to find the density function of z. So we use the convolution method, and this was also given where we have this formula here, essentially saying that the order of integration doesn't necessarily matter. So in this function we have that the integral from negative infinity to infinity of fx of alpha, it's a little bit hard to read my alphas, but fx of alpha times fy of z minus alpha d alpha is equal to fc of z. So if x and y are independent, then this is kind of just repeating what was stated there. So essentially, if we have the convolution fxz and that star symbol and fyz, that's equal to, essentially we pull down what we had here at the top, where the x's become alphas, and so you have the integral from negative infinity to infinity of u of alpha minus 1 minus u of alpha minus 2 multiplied by u of z minus alpha minus u of z minus alpha minus 1. And so then the next line is just that expanded. And so essentially you just FOIL it, so then you have u of alpha minus 1 times u of z minus alpha d alpha minus u of alpha minus 1 times u of z minus alpha minus 1 d alpha, and then again minus u of alpha minus 2, because so you're doing alpha minus 2 times z minus alpha, so it's u of alpha minus 2 times z minus alpha, and then for the last two, they're both negative, so you end up adding the last integral, which is u of alpha minus 2 multiplied by u of z minus alpha minus 1 d alpha. So by expanding that, so when I realized it's a little bit messy, and I realized that it's actually easier to take density function to be u of x minus 1 instead of u of x minus 1 and then u of x minus 2. So you should get the same answer anyways. And so when I repeat these two steps using u of x minus 1, you get the same answer if you just shift it to the right by 1 at the end. But basically you end up with this here at the end. So you have u of alpha multiplied by u of z minus alpha, and again just the integrals expanded, and then when you simplify that you end up with bounds, and to find the bounds you use this trick here. So this beginning of the initial step function is the upper limit, and then the very end of the second step function is lower limit. So here we have the limits going from 0 to z for u alpha multiplied by u of z minus alpha, and that there's equal to 1, and then that's multiplied by uz, minus 0 to z minus 1, u alpha times u of z minus 1 minus alpha, and again that's equal to 1 times uz, and then minus 1 to z is the upper bound of u of alpha minus 1 times u of z minus 2, which is also equal to 1, but this time this is multiplied by u of z minus 1, and then you add the last integral, which the bounds go from 1 to z minus 1 of u of alpha minus 1 times u of z minus 1 minus alpha. This one is multiplied by u of z minus 2. So essentially you just keep simplifying it until finally your final answer when you solve the integral, it should be z times u of z z minus 1 times u of z minus z minus 1 times u of z minus 1 plus z minus 2 times u of z minus 2. And then you shift 1 to the right because it's a little better. Because, as mentioned, I had shifted it to the left in order to make it easier. And so when you shift 1 to the right, you end up with z minus 1 times u of z minus 1 minus 2 times z minus 2 times u of z minus 2 minus z minus 3 times u of z minus 3. And then to solve, that's with the convolution method. So with the geometric method, you end up with p of the variable z is less than or equal to z equals p of x plus y is less than or equal to z. And so basically what that looks like is you draw the line x plus y equals z. Sorry, that goes through z on the x and the y axes. So essentially what you have for z is less than or equal to 1. It's obviously not a scale, so it's just kind of representative. But basically you have what the shaded area looks like a triangle, and so to calculate that area, you make kind of an imaginary square. You just take the area of a triangle where that's equal to the length times the height, which would be z squared, divided by 2. And so basically p of x plus y is less than or equal to z is equal to z squared over 2. And then we take the derivative of that to the probability density function. So the derivative of z squared over 2 is just z. And then we also have the shift by 1 to the right. And so then for z ranging from 1 to 2, we do, again, kind of a representative picture. This time z is greater than 1 on both the x and the y axes. And so you have this distance that is equal to z minus 1. And again, that shaded, I forgot to shade it, but that triangle there, which is the area that we're looking for, is just the area of the triangle. But this time, so what we can do is you take the whole area, which would be the z squared over 2, but this time we're going to subtract that small triangle, which is 2, because we're taking both triangles, so it's going to be 2 times z minus 1 squared over 2. And then that's equal to, when you simplify it, it's negative z squared over 2 plus 2z minus 1. And then we're going to take the derivative of that, and that's equal to negative z plus 2. And then for everything else, we know that when 2 is less than z, then f of z is equal to 1. And so the derivative of that is just 0. So altogether, and then including the shift to the right, we have the density function is equal to z minus 1 times this is the distribution function. So z minus 1 times u of z minus 1 minus 2 times z minus 2 times u of z minus 2 plus z minus 3 times u of z minus 3.